In the previous video, we learned that a sequence converges if it has a finite limit. We also practiced finding the limits of several sequences. In this section, we want to make a connection between discrete sequences and continuous functions. This connection allows us to use the rules of limits for continuous functions to determine the limits of a sequence. Here's the theorem. Suppose f of x is a function and that a sub n is a sequence of real numbers. So pausing right there, we're dealing with something called a continuous function. Just for explanation purposes, let's imagine a continuous function. Maybe the graph of f of x does something like this. Now, on top of the graph of this continuous function, we could locate similar terms of the sequence. If I plot the value of the sequence against its position, so in this case I'm using n on the horizontal axis, and plotting a sub n on the vertical axis, we would observe that the function and the sequence have the same value for natural number inputs to that function. That's what is being expressed right here. The value of the sequence a sub n can be generated by the function f of n, where n is an element of the natural numbers. Remember, the upside down a means for all n in the natural numbers. So when I plug in these natural number inputs, 1, 2, 3, 4, etc., then the function value and the value of the sequence match. The difference between the two structures is that the function f of x is continuous on its entire domain, let's say negative infinity to infinity. So you get a connected, continuous, smooth curve. Whereas the values of the sequence are discrete, distinct, unique points with distance between them on the graph. It turns out that the long-term behavior of the sequence is similar to the long-term behavior of the function. Thus, if the limit as x approaches infinity of f of x, the continuous function equals L, then the limit as n approaches infinity of the discrete sequence a sub n is also equal to L. So the ultimate destination of the continuous function is the same as that of the discrete sequence. So what does all this mean? This theorem allows us to use properties of limits of continuous functions, such as, for example, L'Hopital's rule, to find the limits of discrete sequences. Let's try example 6. Find the limit of the following sequences, or state that the sequence diverges. So the sequence we're considering here is discrete. That is, if I were to plot it on a graph, I would have distinct points with distance between them, unlike a continuous function. But I can determine the limit of this sequence by treating it as if it is a continuous function. So we can look at this as the limit as x goes to infinity of 2x squared over x squared plus 1. I'm using x here to represent a continuous function. In this case, we notice that we have the form infinity over infinity, which permits us to use L'Hopital's rule. So to calculate this limit, I'm going to individually differentiate the numerator and the denominator. We'd end up with 4x over 2x, which reduces to the limit as x approaches infinity of 2, and the limit of a constant is a constant. So the limit of the continuous function, 2x squared over x squared plus 1, is the same as the limit as n approaches infinity over 2n squared over n squared plus 1. In either case, I would end up with 2. Since the limit is finite, we can conclude this sequence converges. Now, on this particular problem, I wanted you to see the connection between the continuous function represented by the variable x and the discrete sequence represented by the variable n. In either case, the execution of that limit is going to be the same. So there's nothing wrong with simply finding the limit as n approaches infinity, as opposed to having to switch it over to the variable x. So let's do that on the next example. To determine if this sequence converges, we need to find the limit as n approaches infinity of n cubed over n plus 1. Notice we can observe on this one we have the form infinity over infinity. That indeterminate form allows us to apply L'Hopital's rule. So we will individually differentiate the numerator and the denominator, obtaining 3n squared in the top and 1 in the bottom. Now, because the numerator is growing without bounds while the denominator is static, then the value of that fraction is approaching infinity. Remember, technically this means the limit does not exist, but generally we describe the behavior of that sequence as approaching infinity. Now, because the limit is infinite, we would say this sequence diverges. Remember that there are two ways that a sequence can diverge. The limit is either infinity or negative infinity, or the limit does not exist. Look at example C. We have the sequence C sub n equals cosine of n pi from n equals 1 to infinity. Now, as n approaches infinity, this argument also approaches infinity. But if we think about the values of cosine as we cycle around the unit circle, they are cyclical. That is, they repeat indefinitely. To see this, as we did on a previous video, we could generate the first few terms of this sequence. Let's suppose that n equals 1. In that case, I would be calculating cosine of 1 pi, which gives me negative 1. If n is 2, we're calculating cosine of 2 pi, which is positive 1. C sub 3, we calculate cosine of 3 pi, that's equal to negative 1. Are you beginning to see the pattern? If n is 4, cosine of 4 pi is equal to 1. So as n approaches infinity, the value of the sequence simply alternates between negative 1 and positive 1, negative 1 and positive 1 indefinitely. So this means that the limit as n approaches infinity of cosine of n pi does not exist. Because the sequence has no limit, we say the sequence diverges. Let's try example D. We have the sequence D sub n equal to arctangent of n divided by n from n equals 1 to infinity. Remember, this is a set of discrete points, not a continuous function. But to determine its limit, I'm going to treat it as if it were a continuous function. So we need to find the limit as n approaches infinity of arctangent of n divided by n. Notice as n approaches infinity, the denominator is also approaching infinity. It is increasing without bounds. But what happens to arctangent of n as n approaches infinity? Maybe a graph would help to visualize the limit of the numerator. If we think about the graph of observe here we are examining the discrete function in terms of, the discrete sequence in terms of the continuous function. We know that the graph of arctangent of x looks something like this, where the asymptote up here is at pi over 2 and down here is negative pi over 2. So looking at our continuous function, arctangent of x, I'm going to write it as inverse tangent of x, we can see that as x approaches infinity, that is, I'm looking at the far right side of the graph, then the function levels out underneath that horizontal asymptote at pi over 2. So as n approaches infinity, arctangent of n approaches pi over 2. Now, if the numerator is approaching a constant and the denominator is exploding without bounds, then that indicates that this limit is 0. Because the limit is finite, we can say that the sequence d sub n converges. That one's kind of an interesting example. So to summarize at this point, if a sequence has a finite limit, then it converges. Otherwise, it diverges. And to find the limit of a sequence, we treat it as if it were a continuous function. Therefore, we have access to manipulation rules such as L'Hopital's rule to evaluate those limits. Another technique that we'll have at our disposal is the use of logarithms. In example 7, we're still looking at calculating the limit of a sequence. We'll use L'Hopital's rule where necessary, and sometimes we'll use logarithms. If the limit does not exist, we're going to state that the sequence diverges. So on example A, we have the sequence a sub n equal to 1 plus 4 over n raised to the 3n over 2 from n equals 1 to infinity. And our goal is to find the limit as n approaches infinity of our sequence 1 plus 4 over n to the 3n over 2. We have learned that when we have a variable base and a variable exponent, we will need to make use of logarithms to separate the exponent from the base. And it is convenient to have an equation in order to legally introduce this new function. So I'm going to set this limit equal to L and then take the natural log of both sides. Recall that if you have a function and a limit operator, those are interchangeable. So I'm going to switch the position of my limit operator and my natural log function. And the presence of that natural log allows me now to move that exponent down in front as a coefficient. Now I don't want to move it in front of my limit operator, since the limit operator depends on n. So I'm just going to move it in front of the natural log. One. Observing that we have a product on the left side, notice as n goes to infinity, 3n over 2 goes to infinity, whereas our argument here, as n goes to infinity, this term is approaching 0, so that natural log of 1 approaches 0. So we have this indeterminate form over here on the left side, which is infinity times 0. That is not necessarily 0, and it does not give us the green light for L'Hopital's rule. So we're going to use an algebraic trick to rewrite the left side in a form where we can apply L'Hopital's rule. Let's write it as the limit as n approaches infinity of natural log of 1 plus 4 over n, and we're going to invert that coefficient and move it to the denominator. Those two changes basically mean I haven't changed anything. I've written it in an algebraically equivalent form. Now, as we've already observed, the numerator is approaching 0, and as n approaches infinity, the denominator is approaching 0. So we now have an appropriate indeterminate form 0 over 0. That allows us to apply L'Hopital's rule. So we can individually differentiate the numerator and the denominator. I'm going to do my main fraction bar a little bigger. My numerator's derivative, we're going to put the argument of the log in the denominator, and the derivative of that argument in the numerator, and the derivative of the denominator, which if you think about the power rule, think of it as 2/3 times n to the negative 1. The derivative would be negative 2/3 n to the negative 2, so I'm just going to leave that 3n squared in the denominator. Now let's clean this complex fraction up by multiplying the top and the bottom by our lowest common denominator. So we're going to multiply by n squared over n squared. And I'm just going to start by correcting the complex fraction in this numerator. So we have the limit as n approaches infinity. Distributing here, we have negative 4 over. Distributing here, we have n squared plus 4n, but we still have a complex fraction. To fix this, 1. Now, let's view this main fraction bar as a division operation. So what we have here is the limit as n approaches infinity of the fraction in the numerator, negative 4 over n squared plus 4n, divided by the fraction in the denominator. Well, when we divide by fractions, we convert the operation from division to multiplication, and then we invert that second fraction. That cures the complex fraction. Now, I'm going to reduce these constants and factor them in front of the limit operator to obtain 6 times the limit as n approaches infinity of 3n squared over n squared plus 4n. Hang in there, we are almost there. Let's recognize one more time that we have an indeterminate form here of infinity over infinity. So we can apply L'Hopital's rule to get 6 times the limit as n approaches infinity of 6n over 2n plus 4, which again is infinity over infinity. So applying L'Hopital's rule one more time, we have 6 over 2 equals natural log of L. The limit of a constant is a constant. Notice 6 over 2 is 3. 6 times 3 is 18. So solving for L, we get e to the 18th equals L. The limit is an important part of this problem, but that's not actually what we're looking for. We're simply looking to see, is the limit finite or infinite or non-existent? So in this case, because the limit is finite, we can make our conclusion that this sequence converges. So we can take it one step further. Because the limit is finite, the sequence converges, and we can say it converges to e to the 18th. Okay, that one was pretty involved. Let's try example B. The sequence in this case is b sub n equals n times 1 minus cosine of 1 over n. And we need to know, does the sequence converge? So we need to find the limit as n approaches infinity of the given sequence. Now, looking at these two factors, as n approaches infinity, we could say the first factor approaches infinity. Observing that this argument approaches 0 as n goes to infinity, and cosine of 0 is 1, then this factor looks like 1 minus 1. So we have the indeterminate form infinity times 0, not necessarily 0. So we're going to manipulate this so that we can use L'Hopital's rule. In this case, we can write it as the limit as n goes to infinity of 1 minus cosine of 1 over n divided by the reciprocal 1 over n. We now have the correct indeterminate form 0 over 0. So applying L'Hopital's rule, we have the limit as n goes to infinity. Now, the derivative of negative cosine is negative sine. Or let's make that negative sign, right? Positive sine of 1 over n times the derivative of the argument, which is negative 1 over n squared. The derivative of the denominator is also negative 1 over n squared. When we cancel these factors, we are left with the limit as n approaches infinity of sine of 1 over n. Now, as the argument approaches 0, that is, as n goes to infinity, the argument 1 over n goes to 0, the limit then approaches sine of 0, and sine of 0 is 0. Because we have a finite limit, we say that the sequence converges, and in fact, it converges to 0. So if I continue listing more and more terms, sorry about the typo over here, that should say n equals 1 to infinity. As I continue listing more and more terms, the later in the sequence we get, the closer the terms will be to 0. Let's try the next example. We have c sub n equals natural log of n squared plus 1 minus natural log of 5 minus 3n squared from n equals 1 to infinity. And we want to calculate the limit as n goes to infinity of natural log of n squared plus 1 minus natural log of 5 minus 3n squared. It would be convenient to calculate this limit if we condense our logarithms. So let's write it as the natural log of n squared plus 1 divided by 5 minus 3n squared. Now let's be very specific on this one. We've used this rule in reverse with logarithmic differentiation. I'm going to switch the limit operator and the natural log. This is ultimately what we were doing on the previous problem with the cosine, but I want to point it out so you're aware of the specifics here. The natural log is on the outside, and we're actually calculating the limit of the argument. Now, as we do this, we can see that inside the argument there, we have the form infinity over infinity. That's a green light for L'Hopital's rule. So we have the natural log of the limit as n approaches infinity of 2n over negative 6n, differentiating individually the numerator and the denominator. Now we can either apply L'Hopital's rule again, or notice that those n's cancel. And inside our natural log here, we then have a problem. We have natural log of, now the limit of a constant is a constant, and 2 over negative 6 reduces to negative 1/3. This is not a real number. Remember, you cannot have a negative argument in the logarithm. So because this argument is negative, the limit does not exist, and we are forced to conclude that this sequence diverges. You can even see it over here in this first term. As n increases, at some point, this argument becomes negative, rendering the natural log to have an imaginary value, or a value that's not real. So this particular sequence diverges. One of the best things about this section is you're going to really get to practice those skills of finding limits. Like on our last example here, d sub n equals the square root of n plus 1 divided by n from n equals 1 to infinity. We want to find the limit as n approaches infinity of the square root of n plus 1 divided by n. Now, just as up here on our previous example, we switched the limit operator and the function, we can do the same thing here, recognizing that the outside function is this square root. So we can write this as the square root of the limit as n approaches infinity of n plus 1 over n. We've used this rule several times, but just to be official, the limit as n approaches infinity of the composition of two functions is equal to f of the limit, whoops, I should be using an x approaching infinity of the inside function. So we're just switching the limit operator and the outside function of the composition. You can either apply L'Hopital's rule at this point, or simply divide both terms of that numerator by the denominator. N divided by n gives us 1, and 1 divided by n looks something like this. Now, as n approaches infinity, this term approaches 0, and the limit of the constant 1 is 1. So my inside limit there is 1, and the square root of 1 is 1. So the limit is finite. Therefore, we can say that the sequence converges, and in particular, it converges to 1.